So, hands-on session on processing LiDAR point clouds. I'll do a bit of an introduction to LiDAR. I'm not sure how many of you are familiar with actually LiDAR datasets. Not at all, I see, so good. And then afterwards we'll dive into some computer notebooks to actually handle that dataset, and we'll both be showcasing geodata frames, a package for saving and reading spatial tables, shapefiles, geo packages, that kind of stuff. And I'll showcase GeoInterface, which is an API package that enables hopefully seamless geospatial operations between different types of geometries in Julia, because everyone has their own favorite type of geometry. But before all that, I would like to ask you to go to the JuliaEO repository, do a Git pull. I think the latest update was an hour ago, so you can decide whether it's up to date or not. And then I would ask you to start a Jupyter Notebook session for this name right here, and then run the first cell. Because the package update and package add, there's a long list of packages that I want to use, and I'm not sure how long it takes, but I think it's good to start before I go to the introduction to LiDAR itself. I'm sorry for the zoom bar. I'm not sure how to disable that. Anyway, okay, then a bit about myself. Like you said already, I have a background in geomatics. I work on Deltaris in the Netherlands. It's a research institute, similar like you have here. It's slightly bigger, but very similar goals. And apart from that, since a year, I'm also an external PhD candidate at U Delft. And my topic is around global terrain modeling using spaceborne LiDAR. And I'll touch upon that topic later in this presentation. So, Deltaris, I've been working there for 7 years. Our mission is basically enabling Delta life, so trying to stay alive in cities, in the global deltas of the world, while there's flooding, sea level rise, and all these other problems. Flooding here in Mumbai. So it's about prediction, modeling. We also have large physical models to do these estimations. And for most of these problems, to tackle these problems, you need a very good elevation data set. Otherwise, you're nowhere. Because if you don't know how high somewhere is or what the slope is, you cannot answer these topics. So elevation data is my key topic and my main research interest. And happily I'm using Julia for that. I think one of the pressing problems, for example, is sea level rise. You have a beautiful, infamous island here. It's Bikini Atoll, so it's known for its atomic tests back when. But also, you can see it here. It's basically a coral reef island. There's a bit of sand, there are a few trees, but this island is not higher than 2 meters at most. So if we do nothing about sea level rise, and probably for this island that won't happen, this island will probably be swallowed in our lifetimes. Unluckily, our global datasets, in terms of elevation, they often measure the surface. Surface meaning top of trees and buildings, or they penetrate somewhat into canopy. So if you would ask a current global dataset of elevation how high this island is, it will tell you it's like 20 meters high in the middle of the island. So that's quite incompatible with doing analyses like this. So for elevation data, you will always go back to LiDAR. And LiDAR is light detection ranging. So it's like radar. I think we have a sort of running joke in all the LiDAR papers and books that they make the most awful pictures of how LiDAR works. Because you probably want to reinvent something yourself, and then you take a house there and an airplane there. I mean, LiDAR is not flown from sort of Boeing. It's often a Cessna or something. But anyway, LiDAR, it's basically you take a laser, and it can be on a total station just next to you, ranging around. It can be on an airplane. Airplane is the most common platform, but nowadays you also have drones. Slowly getting there, it's quite hard to get a drone stable enough to do these measurements. And in the end, we also have satellites now with LiDAR. So the technique in itself is actually, well, it's quite straightforward. You take a laser, you point it somewhere, you measure the return, and then you have a time step, so how long it took for that laser pulse to come back. You divide it by 2, you know the speed of light, and then you have a distance. Of course, for moving and flying airborne platforms, it's quite a bit more difficult and involved, but essentially that's what it is. It's a range measurement. And what you get in the end are many, many thousands, well, hundreds of thousands, billions of thousands of point measurements. And these measurements, they can be anywhere, and they both measure trees, but they also penetrate canopy. Because laser, just like if you shine a flashlight on a wall, it has a very small footprint if you fly from an airplane. So it can actually, just like if you're underneath a tree, you will still see some sunlight through it. In the same way, LiDAR will reach the terrain. So this is one of the few active techniques that will actually reach the ground. Which is why it's such a great technique. If you measure the LiDAR return pulse, it's actually measuring the wave. And depending on how that wave is measured in the airplane, big active instrument, you can either decide of storing the full waveform, so that's full waveform LiDAR. I won't go into that, but you also have those. Often what you get is discretized LiDAR. They take the full waveform that's measured from the laser pulse, and they say on the peaks of that waveform, that's one measurement. That's one big, strong reflection. So then you get detected echoes, and then you would result in 2 points in this case. So that would be 1 for the tree, and it doesn't have to be on the top of the tree, and 1 on the ground. And depending on probably your contract with the LiDAR provider or some types, you can get many more attributes. It's not only X and Y and Z, it would be the intensity of that peak. There can be RGB, sometimes there are optical images taken while flying, because it's very cheap to also have a camera next to the system if you're already flying around the country. And there's the interesting thing of return number and number of returns. So for this pulse you get 2 independent points, but since they belong to the same pulse, there will be 2 number of returns for these 2 points, and return number 1 and 2. And that's a way of also saying last return, which would probably be the ground, if you can reach it. As I said before, there are many, 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 many laser pulses. We're talking about kilohertz often flying around, and you fly around for a few hours. So many, many points, big, big data sets. And all these measurements, they often have centimeter accuracies. Depends on your flying height, type of laser, but it's quite accurate. So unfortunately, very great technique, it's really quite expensive to do this. Mostly because you probably need to put it on a plane and start flying around. And you probably want to make a flight plan, so your airplane will fly around in a certain zigzag pattern so that it has covered the whole Earth. And that's an expensive process. It will, for a country, it will take you millions. And it means that only, let's say, rich countries have done this in the past, made a national elevation data set based on LiDAR, and then also opened it. There are probably some countries who have done this and not opened it, because that's another step. So if you see the distribution, this is open topography. It's an online portal, US based, so they basically try to take in all the US LiDAR data and have some processing tools available for that. Loads of dots in US and all the US constituencies. There's a large part in Europe. I put some pink dots of my own there. So I'm from the Netherlands. The Netherlands does have an open LiDAR dataset where actually, I think last week we published the full AHN4 version. So that's the 4th version of our national LiDAR model. So Europe is following along. But basically the rest of the world, especially Africa, South America, and Southeast Asia, there are no open source LiDAR datasets. So basically we don't have a good terrain measurement in the rest of the world. It's one of the problems I hope to tackle in my PhD, but this is something that's very important. Because if you want to do flooding in Indonesia, you probably have to fly around LiDAR, because there's no good other data sets available. Questions so far about LiDAR and the technique itself? Cool. Because then I like to talk about space LiDAR. which is my favorite topic. So like I said, LiDAR, just lasers. There's terrestrial use cases on a total station, but LiDAR is now also being integrated in cars, self-driving cars. You want to have an active technique to pinpoint people changing modes. It's actually very interesting, I think. In terms of LiDAR technology, self-driving cars are really driving the techniques forward, because in a self-driving car you need to measure a point cloud and then also classify the same point cloud within a millisecond or so, because you want to know that that point is a person or something else. So these LiDAR techniques are getting cheaper and cheaper based on the car technology. Then there's airborne LiDAR, so that's from an airplane, and that's the most default one and especially useful for elevation models. And then since, I'd say, the end of 2018, there has been an earlier one available, but really ISAT-2 and JEDI are two LiDAR satellites. So they put a laser on top of a satellite. And that's great, because then suddenly we have LiDAR globally. But, and that's a big but, as you can imagine, an airplane can fly around in circles, patterns, and whatever you want. But if you want to do the same, you cannot do the same for a satellite, essentially. So there are major differences. For airborne, you can pinpoint the laser. You can try to point it a bit. You can change direction. In a satellite, you don't want moving components, essentially. It can break down and you can't repair it. So what happens is that you kind of move the laser pointer. Also, instead of flying 1 kilometer above the ground, you're now 500 kilometers above the ground. So you need a way different laser to actually still have some good footprint on the Earth. And it zips by at 5,000 kilometers an hour, yeah. It's crazy fast. So these are interesting technical considerations, but the biggest one is that it's the area coverage. So with terrestrial and airborne LiDAR, you're making sure that you cover everything based on your flight plan or other considerations. For spaceborne LiDAR, you just have to be lucky. It will zip past overhead, you have an overpass, you have some measurements, but it will never reach full ground coverage. I will show a picture later. So these are roughly the orbits of these two missions that I'm using in my own research, and they're very useful, I think. ISAT-2, it's meant to investigate ice sheets. So whether the ice packs moving, melting, etc. They're very good at detecting ice lakes, for example, which is an indication of melting. And there's JEDI, which is a full waveform LiDAR. It's attached to the ISS, the International Space Station, and it's actually meant for measuring the biosphere, actually biomass and such in the tropics. But luckily for us, I'd say they're both NASA missions, and they decided not to simply turn the laser off when there are not over ice or tropical forests. They leave it on, so we have measurements all along these orbits. But the big drawback is the coverage itself. So compared to radar, and we've seen a lot of radar processing already in these workshops, is that it's basically, it takes an image and it's probably 50 by 50 kilometers wide, something like that. So after, I'd say, a few months of orbiting, you'll probably have the full coverage of the Earth, because all these pictures are overlapping, and eventually you have at least a single measurement everywhere. I think I remember one presentation that said you have at least, what is it, a few hundred tandem X measurements or so. Great stuff. But since this is LiDAR, it actually it has a footprint not of 50 by 50 kilometers, it's not an image, it's a single point measurement, and it's roughly 20 meters on the ground. So maybe if you have a ISAT-2 point, if it's an XYZ thing, it would probably have measured something in this room. And you can imagine that with such a footprint, you will never completely measure the whole Earth. There will always be huge gaps. So these are two, this is one ISAT overpass and one JEDI overpass. So ISAT is the vertical ones, almost vertical, and JEDI are the more diagonal ones. You see they have multiple beams. It's not a single laser pulse, but it's actually laser pulses and beams. And this is basically the pattern that you get on the ground. ISAT has a smaller footprint, let's say 70 meters. JEDI has a slightly larger footprint of 25 meters on the ground. And the differences in beam patterns. So JEDI is nicely spread out. Every 800 meters there's a beam on the ground. While ISAT-2, they really wanted to bring well, beam pairs close together, 90 meters in between. And that means they can measure slopes on certain surfaces, which also of interest to them for science. So this is how your data would look like if you load it into QGIS.
What are these gaps?
This gaps is basically, this is single overpass. And of course this will fill up, so you probably have a few...
I mean in the trail itself, like there are like the specks of like missing, like you see like...
Oh right, yeah, so there are strong and weak beams. Basically what they do, they split the laser beam into multiple beams. And that's a way of getting more measurements. But of course it has less laser power, so it probably won't penetrate deeply into a forest. So it's a trade-off. So what you see for ISAT, the left track here is the weaker beam, and then you don't always measure the same thing. For example, it's influenced by the sun, but also clouds. It can probably penetrate the cloud, but it will skew your measurement. So I filtered out the low quality measurements here. And sometimes they're not even measurements, because there has to be a reflection back to the sunlight. So that's why there's missing data.
I see.
And yeah, same for JEDI. I believe this is the strong beams of JEDI, and those for the weaker beams, and you can see that indeed in the coverage. Yeah. So this is nice to have. And if you combine this over time, because these have been launched, these two missions have been launched at the end of 2018. We're now 4 years, well, yeah, 4 years of data. They're nearing probably the end of their life as well, these missions. I think JEDI got an extension on the ISS, because basically it's a module you plug in on one of the, I think the Japanese science module. I believe they're now lobbying to get an extension, and another one actually. And ISAT is basically probably continuing as long as their laser is firing. Eventually it will burn out. For the ISAT-1 mission, it was 7 years. So if you combine this over time, you get pictures like this. So there are many, many overpasses. This is an older one. I think this is a picture from 2020 when I made this. It's over Vietnam. You see there are still large gaps of multiple kilometers in between measurements. And this one I made more recently. There's only a fraction of JEDI and ISAT data, but you can see, especially JEDI is covering the Earth nicely, although of course because it's attached to the ISS, it's limited to roughly 56 degrees. So this is the big drawback of space LiDAR. If you have a measurement, it's great, because it's probably the first terrain measurement that's ever been done on that point of the Earth. If you have no measurements, you're out of luck. Then a little bit about the data handling, because this is the package I wrote, spacelidar.gl. It's basically to fix this problem I had. This is a NASA, these are NASA datasets, so they're provided by NASA on their distribution archives. And these are all H5 files. I'm not sure if you're familiar with them. They're like the basis of netcdf files. And they come, so it's not a shape file or a geo package. Binary file with many, many attributes, all array things. So you need to be able to convert this. So I think in the second notebook I will show you how to use the Julia package to convert this H5 file into a simple shape file or data frame actually. And good to know, these datasets, they're getting really, really large. JEDI, I think my estimation of the JEDI XYZ dataset that you could use instantly, it's probably 40 terabytes at the moment. ISAT has aggregated versions, so if you go to the raw version, I think you're at a petabyte right now, so that's, you can only use it on a smaller area in the world, or have a huge cluster or contact with NASA. The aggregated version is probably 20 terabytes. So, well, good data sizes, I'd say. And good to know there's an open altimetry web service, which makes it easy if you just want, you can go there, openaltimetry.org. You can do a very small bounding box selection, and you can see where there's data and where not. So that's a good way of inspecting data before you go into detail with the Julia package and then eventually find out there's no data altogether. And lately NASA has been improving the data access. So they're now also putting this data online in S3 buckets. That sometimes makes it way easier, especially if you want to process this amount of data, you probably just want to process it in Amazon EC2 instead of downloading it to your cluster or workstation. I've used this data together with some colleagues of mine in a paper. So we made a global coastal terrain model, but a very coarse terrain model at a 5 kilometer resolution or even 1 kilometer resolution. And I'd say, but that's the first really terrain measured elevation model. Other elevation models they will measure all the trees that are here in the Everglades. This is part of Florida. So it's and a nice recent paper by my colleagues who used the same data set to show that sea level rise will be worst for the first meter of sea level rise, because that will inundate most. And the second sea level rise from, let's say, 1 meter to 2 meters won't do so much impact anymore. Okay, then this was the LiDAR introduction, let's say. So I'll move to the Jupyter notebooks. Any questions thus far? Okay. So I have 3 notebooks. One is basically handling airborne LiDAR. I've provided in the JuliaEO repository a small LAS file, LAZ. It's an AHN4 sample, which I completely decimated to make it as small as possible while still being useful. The second one is a very small introduction to my space LiDAR package. It's just a utility package. It's basically getting the data in a data frame, and then it's up to you what you want to do with it. And the last notebook, which might be the most interesting to you in a generic sense, is showcasing GeoInterface and GeoData frames. I will be using GeoInterface and GeoData frames a bit in the previous 2 notebooks, but the last one is the more technical in-depth one. I've used all Jupyter notebooks because I thought seeing the latencies we all had in Pluto notebooks. I do like Pluto notebooks, don't get me wrong, but they might be just a bit too slow. So yeah, let's switch. Forgive me, I will be sitting down because I have to keep clicking and typing.
Of course.
Sorry, I have a question maybe.
Yeah, sure.
Before you start. Do you know if it's already being used like this type of LiDAR data set from Spaceboard to increase the accuracy of already available and a bit old data sets about elevation like SRTM that I remember it was 30 meters.
Yeah.
And that's the public use, I think is the best still, if I'm not wrong. I used to do it, work on that like some years ago.
Sure. So yes, you can improve the existing elevation models because they are radar-based, they are full coverage, and then use space LiDAR to improve it. That would be the topic essentially of my PhD. Of course, I'm not the only one. So I think the best current radar model is actually Copernicus DEM.
Okay.
It's based on TandemX. Basically, you have the TandemX mission, then Airbus made World DEM out of it. And now ESA bought World DEM and republished it as Copernicus DEM. So that's the 30-meter global elevation model. And I'd say it's by far the best open model. So also simply because SATM is from 2000.
Yeah.
So TandemX has been collected for at least this elevation data set, I think around 2012 to 2015 or so. So it's also 15 years newer. And you can see that TandemX is actually, 10 meters, 12 meters actually. So 30 meters is resampled, it has been coarsened, but you can still see way more details than SRTM. So I'd say if you want to use an elevation model now, use Copernicus DEM. And there have been already, I think if you search literature, several improved elevation models that try to sometimes use ISAT. I think most it's ISAT. JEDI is a bit, slightly more outliers in JEDI that are harder to filter out than in ISAT. So there have been improved elevation models. Okay, so I go to my browser now to have the notebooks open. Does anyone have problems with actually opening the notebooks, or did you run into errors when running the package add or update?
I cannot install a package. So I'm trying to do it offline.
Okay, which package can't you install, or you can't install it?
It says unsatisfiable requirements detected for package space LiDAR.
Okay, so that's probably your existing environment, and then some of the dependencies want to use a newer, Space LiDAR probably wants to use a newer dependency than you have.
Okay, alright, I'm updating now everything, so we'll see in a few seconds.
Felix, if you could help, that would be great.
Yeah, in the package add also this geostat servers. Because it requires.
You can also just remove Space LiDAR from this package add.
Right, let's see what is happening. Unfortunately, the internet is not faster, so it will take some time.
Okay, so I put all the packages I will be using in here, which is probably a lot, and then it's a bit of a, well, it says something about the state of the package. I'm using point cloud rasterizers here, which is not even registered. Yes?
I think you're missing one, data frames, because I got an error saying I was missing that package.
Fair enough.
On geostat server also.
I think I removed geostats from.
Because after this you are putting using geostat servers, so
You're right. I wanted to be nice to you, but I didn't get to it. You can remove those invocations, and if Space LiDARs are running out, you can also remove it, because it only concerns the second notebook. I just put all of them here to have it installed before we start. Okay, so I'd say if something errors out, just try to remove it from the command line, and then we'll see. So LiDAR point clouds. In the files, I have vlieland.las over here, and that's the .las format is a point cloud format. So it's I think the ASPRS institution, they define certain formats for storing point clouds. And then I believe it was Martin Isenberg, who sadly passed away, who made a compressed file format out of that. And that has become the de facto standard for storing point clouds from airborne LiDAR. And these files are often very big, especially if it's a national data set. I understood that Portugal will be hosting a national elevation data set, or making one in the coming year. So I can imagine that after a national LiDAR survey, they will be cut into map tiles, let's say 1 by 1 degree, or depending on the map size of your national map. But then will probably be a tile of, let's say, kilometer by kilometer. Such a file will probably be a few gigabytes compressed. And uncompressed, it will be tens of gigabytes. So these files probably are too big to fit in working memory for the computer. So that's why I wrote the package point cloud rasterizers, which basically is able to iterate over those point clouds without storing them all in memory. It's a bit slower because I have to pass over all the data twice, but it could handle larger than memory point clouds in that sense. So let's start with using the LAS.io package. So there are many packages like this that basically say extension io.gl. So this package is purely for opening LAS files. I'm using Julia 1.8.5, but I'm not running in Docker, but if you're running Docker and using 1.8.4, it should also work. Okay, and what we then get back is a LAS.io dataset. So this is lazy. It's actually using the LASZip library. Can I help anyone, by the way, because there's a lot of talking?
No, I think for me it's just the computers
Yeah,
down things. So
super slow.
yeah.
Okay. This is just lazily loading. It's not loading all the points into memory. This is just opening the file. It's using the last C++ library in the background. So we can try to see how this looks like. I'm decimating by 100, because otherwise you're plotting, what is it? This is only 500,000 points. And this is already a very decimated sample of the AHM4. Normally, we're talking about millions and billions of points. As you can see, well, very nice that the plots interface works on this. It's not really useful to try to do a 3D plot of point clouds. There are probably too many points for you to plot nicely. So you might want to try Maki, but you could run out of memory. So what you want to do is always, or at least that's the pragmatic approach, I'd say, is try to rasterize your point cloud. Because an image is much easier to display and manipulate than all those points. So let's do that. But before, if you want to look at the points and inspect them, LiDAR implements the tables.gl interface. So you can just use data frames. You could also use another tables package. And if you call that, then you get a nice table with all the points. And then you have some more columns. So you can see the geometry is stored as a static array of size 3 actually. But you also see that we have an intensity, we have the return number of returns. There's a scan direction, which is actually the angle of the laser, which is making. There's moving parts. And there are attributes like edge of flight line. There's even a classification in here. So depending on, I guess, the contract with the LiDAR provider, for Portugal it could mean that the data set that you download maybe in a year's time could already be classified. And then it would depend on how many classifications you get. I know that the Dutch data sets have once been sent to, I think, India to classify them in really many classes. I think they had individual classifications for certain objects on a farm. That might be a bit crazy. Other classifications just include water and ground. That's, I think, one of the simpler ones. So this is already classified, but we're going to imagine that it's not and try to do a classification ourselves to create a DTM essentially out of it. But if you don't want to do that, this is a data frame with everything in there. So you could do all your own analysis on this object. It's a big table, so scrolling. So I talked about number of returns before, because LiDAR can penetrate canopy and you can have multiple reflections. So if you plot or make a histogram of the number of returns, you actually see that, well, most of the data has a single return number. So just reflected, bounced off, that was all you got. Or for some cases, you get 2 reflections, and even lesser cases 3, sometimes even 4. And 5 is apparently in there, but almost invisible. This is also depending on your laser strength. So I think newer lasers can get you even more reflections. I'd say 2, 3, 4, 5 here, so everything above 1 probably indicates that you're measuring canopy, because there are not many objects that you can actually penetrate in a single laser beam and you get multiple reflections back. It's either probably water. If you have a green laser, you could actually penetrate the water column, so you could reflect off the water surface, then reflect on some of the turbidity in the water itself, and hopefully eventually reflect off the bottom. So that could happen as well. So these kind of objects you're measuring. Given this table, this is actually the first demonstration of geodata frames. I'm not telling you anything about it, but essentially we provide geodata frames with the table, data frame, and we save it to freeland.geo package. I'm not sure how many of you are familiar with geo package. I mean, shapefile must just be, we must move away from shapefiles, I guess. It's an older format that's in many ways, well, we know better now, I'd say. So GeoPackage is a nice one, but you even have GeoParquet now, and we're going to GeoArrays, arrows. So this is basically how geodata frames work. It's a one-liner. It just takes a data frame with a geospatial column. which is the geometry column of those static arrays. Note that a geo package, most of the geospatial formats are not compressed. You could probably zip them and get some compression, but natively they're not compressed, meaning they will be much bigger than the original last file. So we're storing exactly the same information, maybe even a little bit less. So the last file is only 7% of the geo package file size. So for these point clouds, don't try to save them all to shapefile or geo package. You will just run out of storage space. Okay, so that's how you basically load a point cloud. So now let's try to classify it. And I'm using point cloud rasterizers. This is a non-registered package by Deltaris. As you can see at the beginning of the Jupyter notebook, we actually added it with the GitHub URL. And I imagine you could also do something like this yourself. Just develop packages on your own GitHub repo or your or other Git instances, and then add them. Nowadays, you can even add your own registry by adding your organization as a Git URL, and then you can work with packages without registering them in the public Julia repository. It could be useful for a research institute. There's a question.
Yeah, no, I'll just add something to it. It's actually quite nice because you don't have to make the repository public. So if it's like a restricted GitHub repo, we'll just ask for the login credentials. So that can be really nice for some organizations if you're not allowed to share code.
Happily, we believe at Deltaris, we believe in open source. We always say dare to share. Of course, you always have friction, and in some cases you need to be on a private repo. But it is indeed very nice that the packages for Julia just work with Git out of the box. Anyway, moving to the point cloud rasterizers. So what we're trying to do is we have all these points. We're basically going to inspect each point. We're going to define a raster, so a certain bounding box and a certain cell size that defines a spatial raster. And for each point, we're going to determine in which cell that point would intersect with. So in which point cell it would fall. We do that for all points. And then we have an index, we have a lookup. So, because point 1 would fall in cell 2 and point 3 would fall in another cell. And that's a structure we could also manipulate. And it's actually something that's okay to store in memory. It's not duplicating the whole point cloud, it's not storing all kinds of vectors, it's just a large list of integers. So this is the invocation, we just call index on the data set. So this actually works directly on the LassIO dataset, but it should work for any multi-point geometry. I'll come back to that later in the geo interface session. We provide it with cell sizes, which is just 1 by 1 here. This of course depends on your CRS of your point cloud. And in this case I know this is the Dutch elevation model, so this is the Dutch coordinate reference system. And I provide that directly here with geo format types. So this is the first introduction of geo format types. It's just a wrapper package. I think Rafael Schouten made it. You all know him by now. And essentially what it does, or what we determined, is often we were passing strings or numbers around to determine coordinate reference systems. Like I'm saying 4326 for WUGS84. So geoformat types just wraps those integers and strings into an actual type that we can dispatch on and say, look, this is not a random string of foo, this is actually a description of a well-known text of a coordinate reference system. So this is the way how you would define an EPSG reference. This would be the Dutch coordinate reference system, but you're probably more familiar with just putting 4326 there. So I hope this is, there are not many points in here, so that's why it's quite fast. But this already would, on normal point clouds, this would already take a few minutes and maybe even hours on large tiles. You will get a progress bar. So this is actually, what we now have is basically a raster of counts. So if we plot that attribute of the index, of course, it's not showing anything. I need to. So what we see here is a rasterization of the point clouds, purely based on the number of points falling into each cell of that raster. So you can actually see a little hardware here. And here there's clearly a larger clump of points, so that's probably trees. Because of the multiple returns over trees, you get more points in such an area. What you can also see that there's a very nice diagonal line in here. And this is a common pattern in airborne LiDAR datasets, where there are multiple flight lines by the plane, and they will also always overlap a little bit. So on this side is probably an overlapping part, and that's why you get twice as high as a point density than the part to the north. We can also say we don't want 1 by 1 meters. I decimated this data set, so I think this is the most high res you can get. But for the original data set, you could go to half a meter or even 25 centimeter cells. We can also, of course, go higher and then just make a much squarer block. You see almost black line here, and that's probably because the bounding box of the data set doesn't nicely align with the cell sizes I chose. So let's go back to 1 by 1 to actually identify features. It becomes a bit hard at 25 meters. So if we want to create a terrain model out of this, you want to actually ignore all the vegetation points, etc. So we're gonna start with only taking the last returns of the point clouds. And the last return, because previous returns are always higher by definition, we probably don't need them for the terrain. So we would define our own function, that is, and that would depend on the actual point object you're passing in. It could be anything. In LiDAR, we know how the point looks like. So we make a function. It can be even an anonymous function if you want. That just takes a point, p, and then it compares the return number with the number of returns attribute of each point. So if the number of returns is 3, then only for return number 3, so the last point, this would actually say true. And then we can call filter on this index we build up with this function. It's actually very quick, and what it does is, again, loop over all the points, compares them, and if it's false, it would actually drop that count altogether. So you remove the index for that specific point. So if you then again plot the index purely on counts, you actually see that it's much more homogeneous because there are no multiple returns anymore. Moving on from that, the last function essentially that you want to apply in this rasterization of point clouds would be to reduce everything. You still have a cell, which essentially is a bucket of multiple points. I want to have one value for that cell. Then you can write it to a geodiff or your other raster format that you're interested in. So we need to apply a reducer to that. And then the reducer would be, we could choose a minimum. So just that would be the minimum of the elevation points that you get. But you could also provide your own function to determine what attribute you would want to reduce. You could provide a function that would choose to reduce on the intensity or some other weird thing. Well, let's first do the min raster reduce. And then we get a geoarray back. This is like rasters.gl. I have a similar package that I'm using here. We could also move to rasters. So now we can save this to geotiff or actually plot it. And this is the first time we actually see elevation in the point cloud. I think there's a bug in Jupyter notebooks with fully zoomed in plots. So you have to zoom in a little bit and then it shows up. So here we actually see the hardware is quite low, and then we actually see buildings here. You can even see that these buildings, typical in Holland, these are slanted roofs. Because it's a little bit orange in the middle. So ideally a DTM, a terrain model, should have these buildings removed altogether. So let's do that. Any questions thus far? Is it working to follow along in the notebooks? Yes. Cool. I see there is also like 6 questions in the chat. Is there any pressing questions from the chat?
If
No?
you want to answer, them, you.
Yeah, I can probably check them myself.
Ah, okay. So
This seems fine.
it's all right. It's okay.
Cool.
It was about the mic. They weren't hearing you, but they are now.
Okay. Via the camera then, directly.
Yeah, it's listening. Okay.
Yeah.
Yeah.
The white pixels on land are white because it's same elevation as water, or because it's missing data?
There are no elevation points inside that cell.
Okay.
And indeed, that also happens over water. LiDAR will reflect on water, but that will depend on the waves or, well, let's say the state of the water. So what you often see in water is that if the water gets more rough, so outside a bit of waves, there is always some angle that would reflect back to the airplane. If the water is perfectly level, you would see only returns on water directly underneath the airplane. So you can actually use LiDAR for water detection. We actually use it for water level measurements and even slopes in water levels. I forgot the English word for that. So that's why you don't see any points here. Normally over land, these white points would indicate that you're really on the edge with this resolution.
Okay.
This is probably still acceptable, but going to a higher resolution doesn't make sense for this data set because your source data isn't better than that. Okay. So we imported the package GeoAreaOps, and there are multiple terrain-like functions there, or for terrains. So there are like slopes in there to determine the slope based on elevation raster. But there are also filter functions. And these are morphological functions like opening and closing on images. And one of these functions is PMF. We can actually check the PMF functions. And that says, this is by the way the help function. I assume by now you're all familiar with it. So just question mark, just like in the Julia REPL on the command line. You get the help function of this function. So the PMF is a progressive morphological filter by Zhang back in 2003. And basically what it does, it takes a raster, assume an elevation raster, and you give it a certain slope, and then it's going to check for each cell whether all the cells around it are within that slope boundary. So if it's, if you put a very low slope in there, most points will be removed if there is any variability in there. It's called progressive because the window size is increasing and increasing and increasing. And this works pretty well. There are simpler ones, but we'll just use this one for now. So we're going to input our minimum raster that we have. So with buildings, and I guess even some trees, these red things are trees. Or at least they don't look like terrain to me. And PMF is going to try to make an elevation raster that's like the maximum allowable surface that it could imagine based on the slopes. So we can just call that. And then we get a maximum raster back and also a Windows thing that we'll ignore now. And if we plot that maximum raster, we'll see that it's different. Everything is a slight bit higher because there's some level of allowance, of tolerance in this filter. We also see it's still allowing houses to be in there, so our window size is probably not large enough to completely filter them out. But what you also see is that there are probably these don't have roofs anymore. So this filter has a maximum in there that limits the elevation, even in the cases where these houses are. So we can use this for comparison with our other raster. And basically, we say from a terrain raster, we can just compare these elevations, and everything where our LiDAR raster is higher than this raster we now produced, we would indicate that as non-terrain. So this would be a binary classification by comparing it. Let's move on. We do see, however, that in this PMF, there are still houses. So we can try to improve this PMF filter a bit by providing better settings. So what I put in here is that I put in a better slope. I put the window size higher and some other parameters. So let's plot that again. And now we get a much better filter surface. So you still see more houses, but all these houses are way lower. So this filter is much stricter. However, it also probably keeps in the terrain features, like there are some dunes here. This is one of the islands in the Netherlands, by the way. So we're going to use this one. And we're going to use this raster to classify or filter again the point cloud index that we have. So we're going to create a new function, a new filter function. And now this filter function doesn't just take one point like before, but it also takes a raster value. So that would be train PR. And note that we're now saying geointerface.z on this point object. And this is the first time we're invoking geointerface. If I want to write it just looking on the points we had, so if I scroll all the way up, the points actually look like this static array and the field geometry. So if I want to write this specifically to this point cloud itself, I would write down, sorry for all the scrolling, I would write something like point geometry and then 3. That's what you would normally do if you only wanted to work for this specific type of geometry. If we want to use geointerface, geointerface has a function that basically gives me the Z attribute of your geometry given a point. So this is the same way, but writing in a much more generic manner. I'll come back to this in the last notebook. And what we define here is that the Z value of this point should be lower or equal to the raster value for which that point is in. So let's define that. And then we apply it. And then we not only filter the index, we also provide it with the max raster. I think this can be removed like this. And then we provide the terrain function. And if we then plot the index.counts, we now see we actually removed almost all the points in all the houses. So this is an indication that our filter worked correctly. But, and that's a big but, we were slightly too strict actually. Because you can see that there's some weird black spots on the right hand side. And you can also see that this dike element, which was protecting the inner land from the harbor, which is at sea level, is also removed. So this is still too strict of a filter. I'm not going to improve it further, but these are this is an iterative process that really needs tuning depending on your landscape. So saying that we're happy, we can reduce this index. It's now completely filtered almost correctly. And then we say, let's use the mean to combine and reduce all these elevation values, and then we can plot it again. And then this is what you end up with. So this would be close to a DTM. The only problem here is that there are still holes in here. So you would now choose an algorithm to fill all these holes. I will skip that for now because I'm thinking I'm running out of time majorly. I'm not sure.
You have until 3:40.
Oh. Well, anyway, that's why I had, I think geostats would be a good candidate to actually use here. Because geostats has many normal solvers like the IDW or other solvers like that. If we have more time, we can go back to that, but for now, I'd like to move on. I think I said We leave interpolating as an exercise. And this is a point that I also want to improve a bit further in the package itself. That would be one of my to-dos actually for coming days. So any questions so far about this point clouds notebook? Because this covered less I/O, less dataset. Now we're moving on to the space LiDAR utility package.
I have actually one question.
Yeah.
So as I understand, we don't make a digital terrain model over the ocean, right? Over the water.
True.
And how to get rid of this noise, this kind of salt and pepper effect in the water here? How to clean this data?
Normally one would just use a vector mask. There's
So you probably use a vector mask and then remove everything that is in that vector, right?
right, yes.
Okay.
But it really depends. LiDAR classification is just a painful task because there are so many points. There are many ways of trying to do this automatically. It would be also, you could also apply machine learning. I think the HN4 is actually partially automatically classified by machine learning, but there always are points that needs a bit of touching up. So I think in the Netherlands, all the houses, we have a very good public housing data set with all the building polygons. So that's an easy step of just classifying all the buildings or removing them from the DTM. For small water bodies, it's much harder. You can imagine that there sometimes are ships in this harbor and sometimes they're not. So that's not one clear way of doing that. You could also look at intensity, because probably most of these water points might have low intensity. If you have an RGB image, it's actually easy to say based on that RGB image to determine whether something is a water body or not. But these are all classification tasks, and it's not that easy. So I have no clear-cut answer for you.
Okay, thank you.
We have used these tools to basically generate DTMs in Indonesia, where we could fly LiDAR for certain parts of the small parts of the country. And then we could use this for basically hydrological modeling. But we only needed to classify ground there, and we're just happy with what we got.
Okay. I have a question. Maybe
Yeah.
it's a stupid question, but so I'm seeing here like the minimum value would be close to 0 or 0, right? Which would
Yes.
be the black color. So when you convert the LiDAR data to the digital elevation data, so how does it find the 0? How does it know it's the 0 is the sea level?
That depends on of course, if you fly LiDAR from an airplane, it's actually probably all with GPS. So those coordinates would be in WS84 to the ellipsoid. And it's up to the LiDAR provider to properly reference that to your national data set, national datum. And that includes a vertical reference level.
I see.
So this has been translated for us to the Dutch national elevation, which is actually, I think, also the reference level for Europe right now, or some offset to it. So this is based on the provider.
Okay, I see. Thank you.
And even here, 0 doesn't need to mean sea level. That's always the tricky part.
Okay.
It's just it has been a reference level, has been chosen. It's based on something, often a fixed reference mark. I think historically, the Dutch reference level was to a lower water level in a harbor, because the low water level is what you want to use for your ships. If it's lower than that, you cannot pass in a certain channel. So it was a classification like that.
So
But
it's an additional thing you might have to play with a bit further to arrive at a good result, right?
Depending on your application, yes. But then I also always say it's better to have a good reference, documented reference, than try to do something yourself to make it nicely match, because probably no one can reproduce that and it becomes harder to interface with other data sets. Okay? Any more questions about this part? Cool. Then let's move on to the second notebook. This is a shorter one, but I'll showcase a few geo-interface functions more. If I run this package update, I think it shouldn't do anything because we installed all the packages in the previous notebook. And this will make use of one of the HDF5 files I also put in the repository. It's one of the smallest ISET files I could find to actually match it. So, oh, it's actually pretty slow. I hope your internet is faster than this. No? Oh, there was a plots update. That will slow down everything for me. Anyway, I'm using the Space LiDAR package here. So this is a utility package. I talked about ISET and JEDI before. So this is a utility package to search and download and basically convert those HDF5 files to, let's say, a tables object, like a data frame. And it can do so for JEDI and ISET, and also for ISET1, which is an older mission. Less data, but could still be useful. So how you would use it is basically call search. You would define the mission, which is ISET. You could also put JEDI here. Then search for the data product. So this requires a bit of knowledge about the ISET products. There's, for example, 8AO6, and then you would look at ICE measurements. That's 8AO3, and that's much rawer data than this. And what we want to do here is provide a bounding box. And this is the first time I've shown extend. So this is the extends package. I think it was also written by Rafael. And this is basically a way of defining a bounding box. Just to get a common interface. Before I was using named tuples with min-x. But then someone else was using a named tuple with x-min. And those are not compatible. So we arrived at this, well, very simple format. You can still criticize it because it's using x and y and not latitude or longitude. But this extend is how you would define a bounding box. So you can provide this bounding box. From the top of my head in WS84, this would mean it's a 1 degree bounding box around this island. So if we call search, this actually calls NASA Earth Data Search. So that's a website where you can search it for manually, very useful. This is the API. And we see here, I'm happy that the internet actually works still. We get 183 ISET2 granules. And a granule is essentially a part of an orbit of ISET2. And because we're interested in only a small area, one granule essentially means one overpass over this area. We have, well, lots of them. Let's inspect one. Just scroll past this. So a single ISET granule, this type, it actually has a few fields. So what we're actually storing is the ID of the granule. That's the whole name with a date and some other information in there, .h5. It actually stores a link to a NASA data center, or actually the National Snow and Ice Data Center in the US. And based on the file name, we derive some attributes, some information. So from the file name, you can actually parse the date. These naming are standardized, so that's useful to filter further. And based on the search results, we also have a polygons that we store, which is this nested vector. This is actually a multi-polygon that defines the bounding box of this granule. If you normally use this with a good internet connection, you can now call download, or even download exclamation mark, the mutating version, on this granule. It will try to download this file from NASA, stores it locally, and then it will update the file link in this granule. So this granule will then point to your local file. Let's not do this, because this is probably a few hundred megabytes. And you also need credentials to actually download from NASA, so you need to have an Earth Data account. It's free to register, but you need to register anyhow, and I'm not sharing my credentials with you. But that's how you would do it. You can use the utility function space LiDAR netRC, exclamation mark, and that would write a small text file to your home directory with the username and password for this NASA server. And that's how tools like curl and wget and even downloads in Julia itself, they would use that file and use those credentials to log into the server to download the file. So I provided you with one of the smallest iSet granules I could find. Normally these are much larger. I think this is only a few MB. So we can use the utility function granule from file and then provide it with the file name. And then we get the exact same thing as we saw earlier, but now it actually has a reference to a local file. Might actually be nice to make it into an absolute path. I'm not sure. And this package, just like the LiDAR package, and I think many other packages in the ecosystem, they implement the tables.gr interface. Basically meaning this is some sort of a table, so it implements a few functions that you can just call a very generic data frame on it, and it will automatically convert all that data on the fly into a table. And I think that's a very nice thing about Julia, all these nice interface definitions, because now at this moment you don't need to know anything about this HDF5 file. You don't need to inspect it, you just call it a table on it, and it will iterate through all this data, even iterate over the multiple tracks there are in that HDF5 file. And then you get the following back. So this is a table with longitude, latitude, we have a height, there's a height error and some other attributes that are in this HDF5 file from NASA. And I think important one is of course longitude, latitude and height, so X, Y, Z essentially. But also good to know there's a quality attribute. And if you want to use this data in your daily work, definitely filter on the quality. Because the non-quality ones, they're just really noisy, never use those. And you can of course do other manipulations based on these attributes. There's also a height reference field, which comes, I believe, from TandemX. So that's how a global DEM would look like. And often, of course, this iSet value is slightly lower than that, because iSet would penetrate the canopy, and whereas the global DEM would not. So we again have a table. This is the same actually like the LiDAR. This is some sort of a point cloud. So we can also, well, let's first plot it to actually take a look at how it looks like. This is not over the Azores. I think the Azores one were too big. So if we call scatter on these columns, longitude, latitude, and color by the height, so we use Z color, we can see that these are the iSet tracks. We can also see that they're actually, you can see a slight curve, as we would expect. And you would see that it covers a large range of latitude, actually. So these iSet granules, they cover really a large part of the Earth. This is a very small one, but they take up, I think, to a quarter of the whole latitude you can have of the Earth in an orbit. So you really need to subset these data sets. You would filter the data frame to get to your location of interest. Even if you downloaded all these 183 granules for Tessera, you really need to subset that data for only Tessera, and you would probably be left with only 1% of the data. So always good to keep that in mind. I remember that JEDI data, the first version, they are now at version 2, but the first data set, they didn't subset their orbits in smaller subsections. And that's fine, but it meant that even if I want to download only a small part of the world, I would get a complete orbit of the Earth. So for downloading the Netherlands, I had to download 50% of all JEDI data ever, which was immense. They improved upon that, so they now have smaller parts. You still need to download a lot of data. So yeah, it's just a drawback of global data sets. We can also, of course, take a scatter plot in the other direction, so actually make a profile. And here you can see much more clearly that we're actually measuring elevation, and it seems that we're actually measuring a mountain or something, because we're going up to 2,000 meters. And I color these by the different tracks. There are 6 tracks in total. It's good to note that even though these files look like they're slightly above 0, they're not referenced against mean sea level. So this comes back to the previous question about what is 0. This is referenced against the ellipsoid. So the WHGS 84 ellipsoid. That's very normal for, well, space data sets, I'd say. But you cannot just start comparing this with your local dam. Depending on where you are on the Earth, you have difference up to 50 meters compared to your local geoid. So you need to apply transformation here. So we can save this. So let's save this to, again, the geo package, my favorite file format. And unfortunately, because I haven't been able to do that yet, this is a table with longitude, latitude, and height. It doesn't specify geometry. So we need to create one based on those 3 columns. So we do that with calling geodataframes create point, which is actually creating create point from ArcGDO. And we do that, of course, in a dotted notation, so this broadcasts over these 3 columns, these 3 arrays. And we write that to the geometry column. So this is just creating an extra column in the data frame, and then we call geodataframes red. And nicely also specify the coordinate reference system. So this is now an extra invocation, an extra argument to geodataframes. And again, geodataframes just takes a table with the geometry column. Doesn't really care about what kind of geometry it is. Of course, it helps if it's ArcGDO, because it's geodataframes itself uses ArcGDO in the backend, GDO itself to write a geopackage. So, and now you have something that you could open in QGIS or your favorite geospatial editor or editing system. Yes?
While saving, got method errors because of type of ArcGDO geometry, in fact.
Did you update
Yes.
all the packages?
Yeah.
Then I will come back to you later and check it. That's good to repeat, also from the previous lectures. If you run into something like this, that's still sometimes quite common. I think if you look at these packages over the past week, there have been multiple patch releases to fix small bugs like these. I love that making notebooks and doing these use cases actually enable me to also find these bugs and fix them. But this is still quite a young ecosystem, so you will find bugs. And also, I think in other languages, it's very clear that you can only do A with B. And here in Julia, we're providing interfaces, and we're basically saying we can accept anything. And there's so many combinations that you'll probably hit bugs because of that. So it's a strength, but it can also be a weakness, and because we're still so young, it's sometimes a bit painful. I think I fixed the bug recently, so might be still an update, but I'll come back to you later for that. And that's it about Space LiDAR, because now you can, it's in a table, you saved it to another format, you can now use this as point data, so you can determine where maybe forests are, or whether your elevation model was wrong or not. Okay, any questions about this? Part that it didn't work with the geodataframe save?
Yeah, sure.
Yeah.
So you mentioned that this was the smallest excerpt that you could find just for demonstration purposes, right?
Yeah.
To your knowledge, what would it take to update the dam from these islands, like these 9 islands? Because we see, like on the mainland, on the continent,
Yeah.
that on something like Google Earth Pro, you actually have like a very nice representation of the height.
Mm-hmm.
But when you go navigate to Azores, it's still like SRTM 30 meters, something like that.
Right.
So to your knowledge, what do you think can be done to improve that?
Well, that would be part of my own research, of course, in my own PhD. But I would say take Copernicus dam. It's more recent and has a better spatial resolution. And then download maybe all ISAT ATOA data. And for these islands, that should be perfectly doable. It's just about trying to find a way of correcting Copernicus dam for these ISAT points. And that really depends on your local topography. you don't have many very high forests, and even the forests that you have, from the limited seeing I've done of these islands, to be fair, they're not huge. So for example, in Indonesia we have problems because the forests can be, and sometimes even plantations, there are kilometers, there are hundreds of kilometers of forest. And here there's clumps of forest.
Yeah.
And most of it is actually agriculture, so that's quite flat. I do wonder, however, how all the small fences, the rock fences, will influence the elevation. So that's an interesting thing to check, actually.
Yeah, that's very interesting, actually.
But I think all ATL data, you should be able to do that on your laptop, providing you have, let's say, 10 gigabytes available.
Yeah, sure.
Something like that. That should be the case. Okay. Last notebook of the day, GeoInterface. So this will be slightly more technical. It can be really helpful for debugging geometries and trying to write more generic code. And if you implement a package in which you have geometry things yourself, it could be actually be beneficial to implement GeoInterface for your package geometries as a developer. Of course, I understand that's an advanced use case. So I'm using geodata frames, GeoInterface. I'm using downloads because I'm still cheating, and I will try to download a shapefile over the internet. It should be a small one, but fingers crossed. And I will be using shapefile. So there are many ways of reading data sets within Julia. LesIO, which I showed you, is actually a wrapper around C++ library to read those files. That's one way, and it means that in the background there's some other project actually compiling that code, writing a Julia wrapper around it, and that's all in the background, you don't notice it, but essentially when you do package add geodata frames, you'll be adding ArchGDAL, you'll be adding GDAL itself, and then GDAL_JOL, which is actually a compiled GDAL version. You probably know this from your Python experience, that if you want to install GDAL and other packages together, Python will not be happy about that. Or Conda will fail on some resolving. So Julia, I think, has very, very nicely fixed it. I'm not saying there will never be errors, but most of the time it's quite easy to install these binary dependencies without huge errors. So if this succeeded, you're actually having a Julia-specific GDAL library already installed, and actually a Proj one as well for project transformations. However, especially in the beginning, we disliked binary packages a bit. So if there was a chance that we could write a native Julia package, so pure native, no C calls, we did. So there's also shapefile, the shapefile package, which reads and almost writes, it's ongoing actually this week, also complete representations of shapefiles. It's the table, the DBF tables that's being updated right now. So there's also native solutions. And geodata frames was basically inspired by, well, many help requests and issues on the ArchGDAL repository. ArchGDAL is a great tool. It makes all the GDAL calls for rasters and vectors much more Julian, but it could be involved a bit to use. Like writing a shapefile, you had to write, I think, maybe 10, maybe 20 lines, and there would often, if there were errors, there would be opaque errors. So I thought, let's make it into a one-liner. It's all using ArchGDAL in the background, but I just made it into a one-liner. So geodata frames can read anything through GDAL. So basically all the GDAL drivers, shapefiles, geo packages, many other formats as well, it can read. So what we're doing here, first invocation, is actually downloading a zip. We use that using downloads.download, which is a built-in package in Julia. Hopefully you're familiar with it. I needed to do a little trick here so that GDAL understands what I'm doing. I'm renaming the downloaded file to shape.zip. So if now GDAL encounters this file, it knows it's actually a zipped shape file. and then it can just open it without me having to unzip the data first and then pointing to the shapefile. So this is the first time, wow, that I have an error as well. So that's also using downloads. It's still erroring. There we go. So this is the first time I call geodataFrames.read. So you just provide it with a file name on your local file system. Like I showed you, it can actually be a zip file. And if you go to the documentation, you will also show you how to actually maybe load data from S3 or online location. It needs prefixes to the file name to actually get there. But basically all the functionality of GDAL is available via providing the file name. And again, we get a data frame. Now with another type of geometry. This is iGeometry, not from Apple, but from ArchGDAL. The I actually stands for interactive. Has to do with pointers and cleaning stuff. But this is basically the representation of the shapefile with attributes, all these columns here. You can see sometimes there's a question marks behind the name, the type here. And it means that some of the values in that column could be missing. Something to keep in mind when editing or using the data. So that's how easy it is to read shapefiles and other files in Julia. It should always be a one-liner, and otherwise we could do better, and please make an issue. Now I want to go a little bit into detail about how this all works and what you can do more with it. So let's call plot on the geometry column. I'm all doing this with plots.gl with the default backend. The plots.gl backend differs per operating system, so on Windows you might have a different backend than here on Mac. But you all should be able to produce a plot like this. So we also support essentially via GeoInterface as well, and these recipes for plotting, we can plot geometries onto a figure. And the rest, well, we can make a histogram of other tables, so this is all straightforward. But now let's look a little bit more into what the geometry actually looks like. So what we have here, we can, I export all the methods operating on geometries in ArchGDAL. So we can buffer the geometry with 1. And then we get a buffered polygon. So we're just making the polygon bigger. But this is a GeoDataFrame specific method actually using ArchGDAL. And like I said before, it's better to write generic code and use geointerface.buffer. In the end, it will call the same method because ArchGDAL implemented geointerface and will use that method. So we can actually say geointerface.buffer in the exact same way. And we apply this on the whole column. And we'll actually overwrite the column in the data frame. So let's do that and then plot it again. Do note that what I'm doing here is maybe you shouldn't do in your normal work, because this is a data frame or geospatial data in latitude, longitude, in degrees. So buffering with a degree is not what you think it is. It's not in meters, it's not the same everywhere. So this is purely for demonstration purposes. Don't sue me. And as you can see, around the equator, this looks sort of okay. Indonesia gets exploded with all its islands, and especially near the poles, everything gets quite blown up. So that's about basically using GeoDataFrames and providing a GeoInterface function. And now I want to dive in, why GeoInterface? What's the real use case? And how does it work in practice? So there's the OGC, which is a standards body. They've provided many standards to use. And one of them was a description of how geometry should interlink. What type of geometries there are. And basically saying that a polygon, if you have a polygon, a polygon actually consists of multiple rings. So a polygon with holes, a normal polygon would have one ring, basically a line string. And if you have a polygon with a hole, it will be two rings. And that's all nested. So we actually implemented that in a traits-based interface in Julia, trying to solve the problem of handling all these different types of geometries in Julia. As I said before, everyone has their own geometry type. I think meshes has its own types and it goes into 3D, so it has a different use case. There's just the ArcGIDO ones, which are direct translations of the GIDO code. There's Geometry Basics, which has been rewritten right now. That's a different use case altogether. Makey probably has its own types, and many other packages have their own definition of a geometry. And that's good, because it's probably optimal for the use case. There have been many discussions in the past about what a point should be. Is that a tuple of coordinates? And which type of coordinate do we allow? Or is it actually a vector of coordinates? In Space LiDAR, which I showed before, there's not actually a point because it's an attribute. There's an x, y, z or a latitude, longitude attribute that would virtually define a point. So we had basically enough of these discussions and just try to provide you with a set interface. So you have a set of functions that you can use and that will unify everything. Because the problem here is, if we look at the geometry that we got back from geodata frames, we see here that apparently this is a polygon, so it has a nice print method, so it can show some of these coordinates. But if I actually want these coordinates as a vector of floats, I don't know what to do, right? Because this is iGeometry. I don't know anything about iGeometry, and probably neither do you. This is someone else's geometry. If we actually try to call the help function on it, this also works on existing instances of types. We see it's ArcGIDO thing, and we see something polygon, so that's good. But we see it just has a pointer. So no way for me to actually retrieve coordinates. This is logical because it's actually calling into C library. So this is a very good use case for GeoInterface because we can actually call all these kinds of functions. I'll provide an example. So the most upper function in GeoInterface is actually trying to see if this geometry implements GeoInterface. So the first question would be, is geometry? And if that's true, then we know that that package author of ArcGIDO has implemented this, and then we can ask further questions. If this is false, we're out of luck, and maybe you should create an issue on the repository. So if this is true, we can ask further questions, and we can ask the geometry trait, and here we see it's a polygon, which we already saw before, so this is something we could infer. But we can ask further questions, like the number of coordinates, and we see this is a 2D geometry, so it just has x and y. There could also be 3, even 4, because that becomes a bit undefined. And we can also request all the coordinates of the geometry, and what we get back is a vector of a vector of a vector float. So this is a bit nasty maybe to work, but this is how this is defined essentially in many geometry formats. And you could save this directly to GeoJSON. So this is what you expect. And this is actually what I wanted. I wanted the vector of points, of numbers, and now I can work with this. However, this coordinates call is actually hiding a bit of the details. So you can imagine you want only the line string of the polygon, or maybe a hole. So you want to delve into the geometry. And again, with the ArcGIDO one, I don't know how to do that, but I know the GeoInterface methods. So I can actually also ask how many geometries are in this polygon. And I get back, I get 1. So it only has an outside ring, essentially. And then we can request that. So there's n geometries and get geometry. And I basically get, with that command, I get now a linear ring, which is what I expected. And that object also implements the GeoInterface. So this is going to nest and recurse all the way down. I'm actually going to show you all of that. So this linear ring that we got. It's a line string trait, so it's actually a line, what you're used to. And again, you can ask that line, how many geometries do you have? And we'll answer 472. So there are actually 472 points in that line. And like that, we can recurse, and we can again ask get geometry for the first point, and then we're going to get a point back. And we can request the coordinates of that point, and then we have a nice vector or float with the x and y attribute of basically the first point in that polygon. So this is how you now can inspect geometries for, I think, 10 custom geometries in the Julia ecosystem. And we're actively expanding the number of packages that implement GeoInterface. So if you use geometries, this is the package to know, or the link to have to the documentation. Any questions thus far? Yeah?
Yeah, so the geometry, it doesn't have any, the GeoInterface doesn't have anything with the coordinate reference system. That's separated in a different package.
Yes and no. Actually, if you see here, this actually says CRS,
Okay, yeah.
so you're quick. So I want to touch upon two other functions. There are actually many more in GeoInterface. I already showed you buffer, and there are other geospatial operations. But let's say two metadata functions are the extend and the CRS. And I've already shown you both, creating an extend object and creating a geoformat type CRS component. And so if you implement GeoInterface, you probably also want to implement extend and CRS in your geometry. And what you see here is that extend is implemented. So I get a bounding box back for this polygon with x and y. But you also see that how many times I even click this, I get nothing back here. It also does show nothing, but let's check it. Is nothing. So this method has not been implemented on an individual geometry. So yeah, sometimes that's just the case. That depends on the package implementation.
Yeah, I have the same with, so if you need a package that just handle like simple coordinates and do some simple coordinate transformations between reference systems, the ArchGDL is the easier way to, like this is only if you need to make your own points implementation and your own geometries.
If you're a package developer, you can implement GeoInterface on all the types that are geometries in your package. But of course, this has a user side. I'm basically the user now. So it's very useful for me to actually get coordinates back like this, or to get the CRS or the extend in my scripts. And the nice thing that it's quite generic, because I basically can switch my backend for shapefile or GeoDataFrame, but even less I/O and even space LiDAR later on, and my code would still work. But of course, you have to check that not everything does have to be implemented. Sometimes the CRS is just unknown. Yeah. Okay. I think I showed writing with GeoDataFrames before, but let's do it again. So we basically loaded this data frame. We buffered the geometry, and we can again write it. So now we write it to test2.shape. Provide it with a CRS, just for the fun of it. And you can also provide a driver option if you want to do exotic drivers, and you can pass arguments to GDAL. That's all in the documentation. But I want to show you that GeoDataFrames actually accepts any tables.gl table and any GeoInterface implemented geometries. So writing is easy because this is still, still ArchGDAL and ArchGDAL geometries. But if I now write this, so this was a shapefile. I write it to a new shapefile, and now we can actually use shapefile.gl. which is a native reader of shapefiles. So let's do that. That's shapefile.table. I get something back. I don't know exactly what it is. Because of course shapefile has a way different interface than what I'm used to. But shapefile itself, just like many things in Julia, they implement the tables interface. So again, I can call data frame on that shapefile object. And I'm really not defining all my packages. I clean too much. So data frames. Of course, we saw this already, but now the difference is that the geometry column in this data frame is now a polygon with 472 points. So not iGeometry anymore. This is actually type polygon. So if we look at the type, we can expect it further. So polygon, 472 points. So again, this is a shapefile specific geometry of the shapefiles package. Don't know how to handle it. This now has, well, parts and points. Points sound good, but still. But because this also implements GeoInterface, we can again just go over it, request whether it's a geometry, and if so, yes, then we can request the coordinates. And this also doesn't have a CRS. And the fun thing now is that we can actually, this is df2 by the way, we can write it to, again with geodata frames, we can write this table. And this is a different table with a different type of geometry, but geodata frames can write it. Which is very nice, I would say. So basically, if you support GeoInterface in your package, you enable much more functionality in other packages as well. So you make it way easier for the users. And basically, if you provide a GeoInterface like geometry, provide the column, default name, that's why it works without specifying it. But if you would put a question mark in front of geodata frames, you would see that there are option geom columns. So we could actually provide it with other options to specify another column in your data frame if you would have named it differently. Of course, this won't work, but maybe your column is named geom or some other weird name. So in the back, what's happening behind the screens, I've got to say, is that this custom geometry, so this shapefile polygon, is automatically converted to an ArcGDAL geometry. So if you want to do that yourself, you can actually call geointerface.convert, just like the base convert, but we call it specifically for geointerface. We say I want to convert it to an ArcGDAL iGeometry, and we give this shapefile thing. And that conversion actually works. So if you implement GeoInterface, you can convert between different geometry representations in the ecosystem. Now it's still a bit hard to actually specify the type of the custom geometry in the other package. But there's now a pull request on GeoInterface. I'm discussing it with Rafael as well, that we can do, I think, something like this, ArcGDAL. We basically provide the module as for the conversion, and then this will work as well. So that's up. That's the new feature that will be upcoming. And that concludes the last notebook I had. So any questions thus far? No, is it all clear? I did see some questions in the chat, or at least there's now 4 more, but I really don't speak Portuguese. So hopefully others can answer whether these were...
It's people complaining about the stream.
Okay, but is that because of me, or is it something...
Maybe I didn't read the whole thing.
Okay. Well, I think it will be fine.
No, it's okay, it's okay.
It's okay.
It's internal.
Okay. Then, thank you. I hope to speak to all of you in the coming sessions or lunches and dinners. And again, really feel free, if you hit some bug or something doesn't work, make an issue. Because otherwise we're probably here now all together. It's very easy to fix some things, and we can fix it by today or tomorrow, and that will help everyone. Especially because Julia is still young, we really need the users and the users to be vocal. Otherwise it's just the user hitting a bug, be disappointed and leave, and then there will be many other users also disappointed. And I can't even fix it because I don't know about it. Okay, you had a question?
Yeah, I have one. Just here on the buffer of geometry,
Yeah.
when you change the 1 degree to 2 to see the size, if you go back to 1 again,
Yeah.
it only increases the size. Doesn't go back to the old image. I can show on my computer also.
Yeah, well, it's mutating, right? We overrode the geometry column. So you basically, you call the buffer on the buffer geometry.
Okay.
So that's supposed to happen, I guess. Buffer. This one, right?
Yeah.
Yeah, basically we have the geometry, the geometry column, and we override it.
Okay.
So it's the buffer of the buffer. So it will be
Always.
bigger each time, I expect. Getting uglier each time. Oh yeah, definitely getting uglier. Yeah, so I want to reset it now. Yeah.
Regarding that, this is all in memory, right? So it's not going to change the underlying shapefile.
True, this is all memory. You really have to call write to actually save the shapefile or whatever representation you wanted to disk again.
Okay. But this could depend on the geometry type you're using, right?
No, I'm using ArcGIS in the background, and that's not lazy. It will load everything.
Yeah, okay.
Of course, if you have your own geometries, that depends on your geometry implementation.
Yeah.
Although I'm not aware of, I am aware of mutating raster packages or lazily loading it, but for vector geometries, I haven't really seen that.
Yeah. I mean, the data is much less.
True. Okay. Then we're going to help someone with their question or their error. I'm going to stop sharing and well, hope to see you again soon.
Thank you.